Good morning, everyone. Let me take off this. So for today, for our Nano at Tech seminar, we have Professor Younan Xia. I want to briefly introduce him. Professor Xia is the Brock Family Chair and Georgia Research Alliance eminent scholar in nanomedicine at the Georgia Tech. He received his BS degree in chemical physics from the University of Science and Technology of China, a MS degree in inorganic chemistry from the University of Pennsylvania, and a PhD degree in physical chemistry from Harvard University. He joined the Department of Biomedical Engineering at Washington University in St. Louis in 2007 as the James McElvey Professor, and then moved to Georgia Tech in 2012. So he's here about 10 plus years. Holding a joint appointments in the Wallace Coulter Department of Biomedical Engineering and the School of Chemistry and Biochemistry. His group has invented a myriad of nanomaterials with controlled properties for widespread use in applications related to plasmonics, electronics, photonics, photovoltaics, display catalysis, energy conversion, nanomedicine, and regenerative medicine. Dr. Xia has co-authored more than 830 publications in peer-reviewed journals with a total citations of over 176,000 and an H index of 208. He has been named a top 10 chemist and material scientist based on the number of citations per publications. He has received a number of prestigious awards, including Materials Research Society Medal in 2017, American Chemical Society National Award in Chemistry of Materials in 2013, NIH Director's Pioneer Award in 2006, David and Lucille Packard Fellow in Science and Engineering in 2000, and NSF Career Award in 2000 as well. This is very important. This is not there in his bio and the website. It was just announced that Professor Younan Xia will be receiving the 2023 ACS Award for Creative Inventions. Let's congratulate Professor Xia on that. Let's give a hand to welcome him, Professor Xia.
All right, thank you, Paul. Okay, thanks for coming to my seminar. Probably I made a mistake by choosing this not so popular topic. But anyway, I'll try to do my best to give you some idea about one of the research projects in my group. And the research I'm going to talk about today has been supported by NIH through 2 R1 grants. And we just got these 2 grants renewed most recently. So we are going to be able to continue this research for another 5 years. And of course, I want to acknowledge supports other than those 2 NIH grants, because over the past 25 years, my research has been sponsored by many foundations and organizations. And in terms of research, at the moment, we have 5 quite different research projects. And the first 3 are mainly related to chemistry or chemical engineering, including synthesis of nanomaterials and the structure property investigation, and also application of those nanomaterials in catalysis and the fuel cell technology. And then for those projects related to biomedical engineering, we have 2 different flavors. One is about nanomedicine. In that case, we develop some carriers or like nanoparticles per se for the controlled release and diagnosis of cancer, for example. And the last one is what I'm going to mainly focus on today is about the design and the fabrication of novel scaffolds for manipulating stem cell differentiation, control neurite outgrowth, and then for purpose of tissue repair and regeneration. And in terms of types of tissues, we are interested in a quite large number of different classes, as you can see over here. And as limited by time, today I can only talk about 2 of them, the tendon-to-bone insertion site in orthopedics, and then peripheral nerve for sciatic nerve repair in that case. At the very end, I will show you one slide about dural matter engineering or repair. And tendon-to-bone insertion is very important in many, well, let's say this way. Okay, it's a very important connective tissue, in particular related to like a rotator cuff in the shoulder, actually. The major issue over here is this rotator cuff could be easily torn, actually, okay, during sports or maybe when you get older. Yeah, this is going to be become a major issue. And whenever you have problem, when you go to hospital, the surgeons typically will just attach the tendon to the bone, okay, and then suture them together. And in many cases, you can have temporary recovery, but eventually this junction is going to rupture again, okay, so that's going to be reflected over here. The failure rates of rotator cuff repair could be almost like 94%, okay, so that means majority of these repairs will fail actually in a few years. And this, of course, there's a reason why that's like this. If you take a look at the tendon to bone, actually, these two quite different materials. If you try to attach them together, of course, when you are involved in motion, the strain is going to be concentrated at the interface because tendon is relatively soft material, bone is kind of hard material. So stress is going to be concentrated at the interface. So that will rupture the interface very easily and quickly. And in the native system, actually, our body solves this kind of problem by developing this so-called insertion site or junction, in which we don't have a very sharp interface. Instead, we are going to have a gradual transition from tendon to bone side. Okay, if you look at this junction carefully, you are going to observe quite a gradual change in terms of structure and cell phenotype and composition, so on and so forth. So for example, the tendon or the collagen fibers on the tendon side is going to be well aligned, and also they are going to just be collagen fibers without mineral coating on it. If you move to the bone side, of course, these collagen fibers tend to be mineralized, will be covered by hydroxyapatite, this kind of mineral materials. And then in this, and the order, of course, is going to be lower compared to those collagen fibers on the left, on the tendon side. And then you are going to have a gradual transition. So basically, by building this gradual change or gradient, that can allow us to accumulate or to accommodate that stress that could be accumulated at this interface, eventually make this junction very robust. So here just show you some additional data just to convince you we do have a transition, we have a gradient in this, at this junction. If you take a look at the mineral composition, this is done using a Raman spectroscopy. You can see the gradual change of mineral phase from tendon to bone side. You have a gradual, almost linear change. And this is like a tissue structure. So you can see the mineral size and the unmineralized region. You're going to have this kind of seamless transition overall. So in order to address the current clinical challenges, we have to find some scaffold materials that can replicate this kind of transition zone over here. So that has been our goal. And for peripheral nerve, as we know, our body is really a network of this peripheral nerve system. We have basically 43 pairs of sensory and motor nerves actually that connect from the brain and the spinal cord to different parts of your body. So that will control the sensation, motion, and of course, this kind of like functions, okay, of your body. So it's very important, okay. So in this case, if there's injury, like damage, of course, that part of the body will lose the function because the brain won't be able to give them instruction anymore. So in this particular case, we are trying to focus on the anatomic structure of the nerve, try to replicate the specific vascular structure of the nerve. Basically, if you look at nerve, it's not just a single nerve. It's going to be divided into multiple nerve fibers, actually. And they are also going to be bundled together from these so-called vasculature. This is particularly important for big nerve, for thick nerves, okay? So you don't have just one bundle, you have multiple bundles arrayed in this way that can easily provide the function, okay, over long distance. Let's start with this rotator cuff repair or tendon-to-bone insertion. When we started this research, I was still at Washington University in St. Louis. We found a collaborator in orthopedic surgery, Professor Samopoulos. Actually, we are continuing our collaboration nowadays. At that time, our idea was kind of like naive or simple. Okay, we just think we can develop some patches. This patch will have gradual change in terms of mineral content. And then this patch can be applied to the top of the tendon when tendon is sutured to the bone, okay? And the gradient in this patch will be able to guide the differentiation of cells, and eventually will help us to build a strong transition over here. That was really a simple and kind of naive idea. So we developed a method to fabricate this kind of like mineral gradient patches. And the idea is quite simple, as shown over here. You just take your scaffold, you just position in this orientation, and then into this container, you are going to add a solution. This is going to be 10 times concentrated stimulated body fluid. It's the solution that's already highly concentrated in terms of mineral composition. So that's why when you drop them into this container, actually there can be nucleation and the growth on the surface of the scaffold. So you can have mineral being deposited onto this scaffold. And by adding this solution drop-wise, and the liquid level, of course, will increase gradually from top to the bottom. So you can imagine the region at the bottom will have a longer deposition time than the region at the top of the scaffold. So naturally, you are going to build a gradient, okay, along this vertical direction. So that's basically the setup. As you can see over here, you have some scaffolding materials put on a glass substrate, and then you add the solution from the top, and then you're going to build a gradient. So here just show you SEM images we took from different regions of the scaffold. This is from the bottom region, okay, very bottom one, and then you move upward, okay, in this direction. So you can see when you move to the top, eventually you are going to have very little deposition of mineral. So in this particular case, we are using electrospun nanofibers as the basic structure for the scaffold. And then onto the surface, we deposit this hydroxyapatite mineral phase in the gradient, in the spatial gradient. And we also tested their mechanical properties, as you can see over here. Depending on the average stress, okay, we applied. And basically, you can see this is a region with a higher level of mineral coating. And this is a region to the right, you have least amount of mineral coating. So as you can see, in particular in this case, at a high stress level, the strain is not going to be just, well, you are going to see the gradient in terms of strain, okay, on the surface. Okay, that's also going to be reflected by the gradient of the mineral phase on the surface. And here you can see the correlation. Here is the composition of the mineral content from the left to the right side. You have more mineral coating than the right side. And the modulus, of course, we measured on the left side, you're going to be higher than the side on the right side, right? This difference could be almost like 100 times or 2 orders of magnitude in terms of difference. And then we culture stem cells. These stem cells were isolated from adipose tissues, and then we culture the seed onto this scaffold, and we culture them. We compare again four different regions with the mineral coating increased from 1 to 4, these different regions. Okay, so basically this is just shown in this curve. You see the calcium content increase in this way. And after culture for 7 days, and this is 14 days, we can use 2 different types of markers to see how the cells have differentiated, right? Specifically, we expect formation of osteoblasts actually in the region with the highest density of mineral. Okay, so this is from this RUNX2. This is a RUN-related transcription factor 2. That's about, it's like an early marker for like osteoblast actually. So you can see from position 1 to position 5 along this curve, indeed, you're going to have gradual increase in terms of differentiation of the stem cells into osteoblasts. And this is also consistent using another stain. In this case, we use osteocalcin. It's a protein actually that will bind to hydroxyapatite. It's like a late marker actually for osteoblasts actually. So again, you can see the gradual change from position 1 to position 5. So this is just consistent. When you have more mineral coating on the surface, you are going to have a higher level of differentiation into osteoblast. So that's really what we expect to have. And then we apply this to some in vivo studies. We were using like a rat model actually. Okay, in that case, you are going to create a defect by detaching the tendon from the bone, and then we are going to suture them together with the scaffold. We call this a patch-based scaffold. We compared 4 different groups. Okay, the first group is just a control. You just use suture, just what we are doing at the moment in the clinics. And then we are going to have acellular scaffold. You only have the mineral coating ingredient without adding the stem cells. And then you have a cellular group. You are going to have patch plus the stem cells. And the last group actually is also a cell-based scaffold, but in this case, the cells have been further transduced with BMP2. It's bone morphogenic proteins. It's kind of like proteins that can, it's kind of like a growth factor actually that can enhance osteoblast differentiation. Unfortunately, when we compare the performance of these 4 groups actually by different measures, we didn't see much enhancement, okay, when we apply these patches and with the cells. And overall, like 28 days or 56 days, if you compare these 4 groups, actually, the cellular group, there are some marginal improvement compared to like acellular group, but overall compared to the control with just the suture, actually, you don't see too much difference, okay? And then we analyzed this problem. We realized maybe this kind of patch is not a good idea actually to use at all. And when you apply this patch onto this repair site, and the stem cells in the surroundings can only really see the surface, okay? They don't really see the region between the tendon and the bone. So that's why eventually the junction is not going to be repaired or as we would expect. So knowing this problem, we switched our directions. We are now developing a second generation of scaffold. In that case, this scaffold is going to be something like a disc. And this can be inserted between tendon and the bone, and then you suture them together. So in this case, this scaffold will have a direct influence on the cells between the tendon and the bone. And we think this may probably give us better like performance in terms of efficacy. So that's the second generation scaffold we are working on. And to make Of course, this scaffold, again, has to have a transition in terms of composition and the mechanical strengths along these vertical directions. Okay, that's basically the original concept. You want to bridge the tendon and the bone with this gradual transition in terms of mechanical properties. And in this case, we rely on the formation of something we call density gradient of nanoparticles. These nanoparticles are just hydroxyapatite nanoparticles you can commercially get from Aldrich. And you mix them with a polymer like PLJ, PCl, this kind of polymer. And by using some tricks, actually, you can control the density of these nanoparticles. So eventually, they can form a linear gradient, almost like a linear gradient along these directions. And now we are exploring two different approaches to achieve this kind of gradient. One of them is just a brush coating. Okay, you can take the solution of this hydroxyapatite polymer mixture, and you coat them. Okay, just like we can use even like a nail brush actually. Okay, for cosmetics. The first layer will contain the highest concentration of mineral, and the second layer you are going to reduce the content of mineral phase, okay, and then you gradually reduce, and the top layer is going to be just a pure polymer. So you can see by divide them into like multiple layers, each layer can contain just one concentration of this hydroxyapatite nanoparticles. So eventually you can create a gradient, even though this may not be a continuous gradient. There might be it looks like a step function, but overall you are going to have this gradual transition from high mineral content to low mineral content. And this, of course, you would argue is not a highly reproducible method. Brush coating, after all, depend the pressure you apply, the amount of liquid you apply, eventually the thickness and of the film may not be so well controlled. So that's why recently we switched to spin coating. That's really the most widely used technique in microfabrication lab, right, to make very thin polymeric films. But in this case, we are using a mixture of hydroxyapatite and this polymer solution, and you can do spin coating layer by layer again. Okay, so from bottom to the top, the concentration of the mineral phase is going to decrease, and in this way, we can easily control the thickness, and we can have a very robust method, okay, to control the both composition and the thickness of this. And here just show you the cross section of the film we fabricate either using brush coating or spin coating. Actually, it's relatively uniform, but you are going to see some gradient in between. Actually, over here, I'm going to show you some more details. And first, just show you the reproducibility. Actually, you can have very good way. Very high precision to control their thickness. Okay, this is 2 layers of coating. This is 6 layers. So every layer is going to be able to give you about 10 micrometer of coating, actually, either using brush coating or spin coating. And when we do spin coating in particular, there's another advantage, actually. You can spin coat on a pretty large wafer, and then you can punch them into small discs, actually. Each one of them could be used for one repair, actually. So that's why this kind of like parallel fabrication, you can generate this kind of identical scaffolds just in one fabrication. This could be like a 30-20 or this kind of almost identical scaffolds for next step applications. So let me show you one example. This example was developed like 4 or 5 years ago. At that time, we are trying to combine this kind of scaffold with another type of scaffold we call inverse arbor. It's like a highly porous structure that could be made of hydroxyapatite nanoparticles. So eventually, this red region will be inserted into the bone, actually. And this gradient and region will be the intersection, and this green region will be basically into the tendon. Okay, so you can suture them together. Okay, as I mentioned earlier, this transition is the most important thing. So as you can see, you do have this gradient formed by using a brush coating. And when you measure the concentration of calcium, for example, you do see more or less linear transition there. And we also measure their mechanical properties. If you cut this scaffold, and in that particular region, you can do elemental mapping, you see the gradient. At the same time, you can use the AFM indentation to measure the local mechanical strength, the Young's modulus, actually. As you can see, when you go from the polymer side to the mineral side, actually, you do have a gradual increase in terms of Young's modulus. That could be increased by more than like almost 10 times actually in this way over a distance of only about, this is not the distance unit, actually it's just the position along these directions. This is about like 10 micrometers, actually it's relatively thin regions. And the top layer is going to be patterned using micromachining actually. In the IEN actually they have this nice capability to machine these arrayed channels into this film. At that time, actually, we only had this CO2 laser, actually. So the precision and capability was not perfect, actually. But you do get a pretty small size, about like 100 micrometers. And, but the surface will become very rough. Okay, this could be improved now by using a different type of laser. Okay, but at that time, this was pretty rough. This was the top surface, and this is the cross section I've shown over here. This is going to be the pores in this inverse orbit scaffold. And then we seed this scaffold with adipose-derived stem cells, and then we look at their differentiation actually. In this particular study, we look at two different types of markers. One is RONX2, that's for the indication of osteoblasts. And then we also look at sclerosis. This is a different type of marker. This is the marker for tendon, actually. So this is just the 4 different regions along the cross-section. So you can see when you move from the polymer side to the bone side, actually, you are going to see gradual increase in terms of green intensity. That's osteoblast, actually, numbers. And this red one, you can see the opposite trend, actually. Okay, so the tendon side, you're going to see more tendons. The polymer side, you see more tendons. And bone side, you're going to see very few tendon cells. And most recently, we further simplify this kind of idea to fabricate this gradient scaffolds. We find that you can simply take a polymer solution, in this case the PCl, and you place it on top of another film that's made of a composite film, right? It's have hydroxyapatite and the PCl. You just put this together, you heat up a little bit, and well, no, not heat up, I'm sorry. You just take the solution of this polymer on this film, you precast, okay, on the dish. And then during this aging process, the solvent will be able to penetrate into this PCl composite film underneath. So at the same time, the PCl polymer from the bottom can diffuse into this solution phase. So at the interface, eventually you're going to form a gradient in this way, okay, through the interdiffusion of hydroxyapatite particles and the polymer chains, okay. And this is like a piece of film, basically, and then we can come to IEN to do micromachining. So we can generate arrayed channels all the way through this film. So eventually, we are going to just use this film as the scaffold. Okay, in this, at the bottom, you are going to have high concentration of hydroxyapatite, and top you are going to have polymer, and in between you are going to have a transition in terms of mineral content. Okay, so that basically allow us to control the differentiation of stem cells you seeded onto the surface of these channels. And this kind of fabrication technique, there's another advantage actually. Okay, if you look at the cross section of these channels, it's not kind of like a straight walls actually. They are going to have this particular like a funnel shapes. This is going to be unique when we apply this between tendon and the bone. They can form sort of like interdigitated like tissue structures that can further enhance the mechanical strength of the repair. Okay. So here, just show you what we are trying to do in the next step. So basically, we are going to have this kind of scaffold that will be basically sutured between tendon and the bone. And this side with polymer in dominance, they are going to just control the differentiation of stem cells into tendon cells. And the bone side will become like osteoblast. In between, you are going to have a gradient. So that's really the control, the nice control we can have. And here, just show you some characterization. Okay, we made. This is a cross section. You can see the gradient from the EDX mapping. The calcium concentration will increase. And in particular, it's very nice. Now we can generate this kind of junction with relatively like thin thickness that can really match the native transition side. Okay, that's typically about like 50 micrometers. It's a very thin layer actually overall. And here is the SCM image of the top and the cross section of this film. And in this case, we already switched to the femtosecond laser in the IEN. Actually, that can provide much better resolution when we do this kind of laser micromachining. And then we can also categorize this cross section using Raman mapping. Okay, you can map, for example, two different functional groups. One is this CO2 group. Okay, that's for the PCl, this polymer. And then you have phosphate group, that's for hydroxyapatite actually. So you can do mapping. Eventually, you can generate this kind of map. You can see have a gradual change of mineral content from the bottom to the top. And the PCl concentration also decrease from top to the bottom. So it's like opposite, like a gradient for these two different materials. So when we seed, again, stem cells onto this scaffold, and first we can see the cells are pretty happy on this scaffold. So you can see increased differentiation, proliferation for these cells as a function of time. And then we also look at their differentiation. Okay, so in this case, we are using a different type of marker for the osteoblast. It's an alkyne phosphate marker. So you can see the gradual change. When you move from the top to the bottom region, you are going to have gradual increase in terms of ALP levels. So that indicates increased osteoblast formation. And here is, again, this is like an early marker actually for ALP. And here we are using a later marker, actually OCN osteocalcin marker. So in that case, you also see this similar trend actually. From top to bottom, you're going to have increase in terms of osteoblast generation. So now we are moving into a second phase of study. We just got the grant renewed. We are going to apply these kind of scaffolds to a different animal model. In this case, we are using a rabbit instead of rats. It's still in collaboration with Professor Samopoulos at Columbia University. He moved to Columbia a few years ago. And in that case, rabbit will provide a much better clinical relevant animal model because the size of this tendon-to-bone insertion site is going to be much bigger than rats. Rats is just difficult to do the surgery. Okay. Now let me switch gears to talk about the second type of tissues we're trying to repair. That's basically going to be the peripheral nerve repair. And currently in the clinics, autograft is really the standard. Okay, if you have damage, due to trauma, accident, or whatever, the damaged nerve can only be repaired by suturing a segment of, a different nerve harvested from the same patient. Okay, so that basically eventually will able to regenerate the connections through this nerve. And autograft, of course, is good in a sense. The nerve is harvested from the same patient, so you don't really have like immune rejection or this kind of problem. But at the same time, it's a self-destructive process. You have to, sacrifice some nerve, maybe from some less important parts of your body, but still you're going to sacrifice, those functions. And also, when the damaged nerve is thick, you have to harvest pretty long, less important nerves from your body. So that's really going to eventually create some secondary damage, actually. Okay, and so that's why people are interested in developing a different type of concept. In that case, try to impose a nerve guidance conduit through this gap, and then somehow promote extension of nerves and cover the gap, and eventually recover the functions. So this concept of nerve guidance conduit has been around for several decades. There are some commercial products in the market already, but most of them don't have a good outcome, okay? Because right now, this kind of conduit is just like a piece of polymer tube, actually. In many cases, they don't really support the growth of or extension of axon nerves, actually. So that's actually has been problematic. In particular, when this gap is large, like typically like 40 millimeters, and this kind of tube definitely will fail. So as a result, people are interested in developing second generation of nerve guidance conduit. In that case, we want this conduit to be porous on the surface of this wall, so that allow the transportation of nutrition, waste molecules, and so on and so forth. So you do really want this to be highly porous, actually, for the wall. At the same time, you want this wall to be decorated with some physical features that can guide the extension of neurites, okay? And also you want to present some cellular cues or bioactive molecules. This could including Schwann cells, for example. That's very important for nerve regeneration. And also you want this to be multiple channel instead of just a single channel. This is particularly important when you deal with thick nerves. When you treat thick nerves, if this lumen is too big, actually, eventually the impact from the surface will be lost, so you won't have any guidance at all. So in that case, this nerve will become tapered when they grow into the middle point of this conduit. So all of these are just basically some general ideas we have to follow when we design these conduits. And specifically, we are using electrospinning to fabricate the scaffolding materials. Electrospinning is kind of simple technique. It has been around for more than 100 years, probably you know it. The idea is simple. You just take a polymer solution, you put in a syringe, and when the polymer solution comes out from this metallic needle, of course, you are going to have a droplet, more or less spherical shape, right, because of surface tension confinement. However, if you apply high voltage to this needle, that needle will be able to inject charges on the surface of the liquid droplet, and eventually you are going to create a very strong repulsion on the surface. So that will lead to the formation of a liquid jet due to the electrostatic repulsion from these charges. And this jet will be basically continuously ejected from this liquid droplet, and when their size becomes smaller because of this stretching force coming from this electrostatic repulsion, and eventually the solvent will evaporate quickly, the polymer will precipitate out as fibers. So it's a very simple idea. It can be applied to many different types of polymers to generate these very thin fibers. Could be from 20 nanometers all the way to several micrometers. It's a very broad size range. So you can control the voltage used, polymer weight, molecular weight of the polymer concentration, and the many parameters. You can have a very good control over the diameter of these nanofibers. And specifically, quite a long time ago, actually, we found that we can also have these fibers aligned, okay, in a way rather than have this random morphology. And the idea is to use 2 electrodes to collect the fibers. So they are going to be an insulating gap. So across this gap, you are going to have fibers coming down to create a very strong stretching force, because these fibers are still charged. So they can induce opposite charges on these 2 electrodes. So you are going to induce a very strong stretching force. So the fibers will be aligned basically across this gap in these perpendicular directions. So here just show you some idea, right? This is the fibers being aligned in this way. This is the SCM image. You can see they are pretty well aligned, okay, even though it's not like perfect. But overall, the fibers are going to be uniaxially aligned. And this is a region on the electrode. You can see fibers still take a random orientation. And here just show you the this edge. Okay, so you can see the fibers do feel the strong stretching force when they're moving close to the edge. The fiber was along this direction, and then suddenly feel the stretching force. They are stretched across the gap. This is the gap, okay, over here. And now we can easily generate align the fibers over long distance by using a very simple device. This simple device is fabricated using a piece of metal. You take a piece of metal, you just bend it into a U shape. So these 2 edges basically can serve as the electrode to collect the fibers. The fibers will be stretched across these 2 edges. So you can have multiple of them stacked together. So eventually you can align the fibers over a pretty long distance. This is about like 10 centimeters actually in this way. Okay, that can be aligned pretty easily. And for those of you, if are interested in electrospinning and electrospun nanofibers, we have major review articles over here published 5 years ago. You can take a look at it. And these nanofibers are pretty ideal to guide the extension of neurites. We use this particular model system of dorsal root gallin isolated from chick. Okay, so you can just culture them on these nanofibers. If the nanofiber has a random orientation, the neurites are going to be projected into all different directions. There's no preferential orientation for these neurites. However, if you culture them on uniaxial aligned fibers, I'll show you on previous slide, the newly formed neurites will be extended along the fiber directions. The fiber is aligned in this direction. So you see the physical guidance from the nanofibers. And you can, on the surface of these aligned fibers, you can add another laminin layer, actually. That's kind of like adhesion proteins that can further enhance the extension of neurites along the fibers through a combination of physical and biochemical cues. And you can also use some fibers that has good electrical conductivity, like Peripheral. This is conductive polymers. And you can also apply electric field. So in this case, you can have electric field and the physical guidance to have this neurites extended over a very long distance. This is like a centimeter of distance. Okay. In reality, these fibers can also be deposited and into different patterns, and that can control the neural extension in such a complex way that eventually may be possible to form neuron circuits actually in this. But that's not the current interest in my group. Right now, we just focus on peripheral nerve repair. And as I mentioned earlier, one of the major requirements for peripheral nerve repair is really the Schwann cells that eventually will form these myelin sheaths over the nerves, and that actually is very important to provide them with the right functions. And so that's why in one of the early studies, we tried to seed the electrospun fibers with Schwann cells, and then we culture DRG on top of it. So as you can see over here, these Schwann cells and these neurites do interact very favorably. Actually, they can form a layer around it. And so that's why we move one step forward, try to apply this to in vivo studies. And we are going to fabricate these conduits, okay, that can be used to bridge the two ends of the damaged nerve. And we use this bilayer design at the beginning. We have aligned fibers, and then we have random fibers. We choose this bilayer structure for a reason, because you want your conduit to eventually have good mechanical strength too, not just the guidance for neurites, right? So that's why when we put these aligned fibers on top of these random fibers, and then you roll up and seal them at the edge, that's basically going to be the conduit. This conduit has porous walls that comes from the natural deposition of the fibers. And on the inner surface, you're going to have these uniquely aligned physical structures that can provide the axonal regrowth, okay? So we did this with a rat model for sciatic nerve repair. Here just show you what we did. You have, basically you have to create a defect, okay? In this case, the defect is about like 10 millimeter long. And then you're going to just graft this conduit across this gap, okay? And then you wait for like typically like 2 months, and then you harvest this repaired nerve and do analysis, okay? So here just show you the comparison of 3 different groups. And one is for the isograft. Isograft is just suture back this graft, this nerve defect. Okay, so that's basically going to be the original nerve. You just take it out and put it back. So that's going to be the isograft. And one group is going to be the fiber-based conduit, and the other group is going to be conduit plus Schwann cells. Okay, so as you can see, for this group in particular, actually the performance is pretty good, impressive actually compared to the isograft. Isograft is the maximum performance you can expect, right? So in this case, if you count the number of nerve fibers in that cross section, actually you can see for this group, actually this is going to be the middle point, and this is going to be distal. Okay, distal is this, middle is over here. So you can see at least for the middle point, actually the number of nerve fibers is almost like half of the autograft or isograft. Okay, it's not perfect, but it's going to be significant improvement compared to just nerve, the conduit itself without Schwann cells. So you do see the positive impact coming from the Schwann cells. The only problem over here for this particular study, the Schwann cells were isolated from healthy nerves. So again, you had to sacrifice the nerves, okay, in order to harvest these Schwann cells. So that's, again, you have same drawback or as autograft, okay, so you have to sacrifice some healthy nerves. So that's why move forward, we develop another approach. Try to take bone marrow stem cells and differentiate them into Schwann cells. And then we can use that as the source, okay, for our repair. Okay, it's almost there. So in this case, we look at how we can control the differentiation of bone marrow stem cells. Actually, we look at the different conditions. The result is that under the right conditions, like the diameter of the fibers and the surface composition, for example, you put a laminin on the surface, you do observe very significant differentiation of these bone marrow stem cells into Schwann cells. So that's a very promising. And finally, we we develop a new design for the conduit. Basically, we're going to take multiple single tubular nerve guidance conduit and assemble them into an array. We make these multi-tubular structures. And what's the advantage? Well, here we can easily target thick nerves. Depending on the diameter of the nerve, you can increase the number of these single tubular conduits, actually. So you can really have good match for that. We can also differentiate bone marrow stem cells inside these multi-tubular scaffolds. Okay, so we have demonstrated that there's no difference compared to the single tubular ones. We also have started to evaluate their efficacy. We first started with this tri-tubular conduit because the model we used was just a rat. It's very small, relatively small nerves. We cannot accommodate 7 conduits. We just use 3. And as you can see over here, this is the 3 individual conduits. And this is the control group, is autographed, actually. You can see the final results. This is a cross-section of the repaired nerve in terms of density of nerve fibers. It's not too bad, actually, compared to the autograft. Okay, you do see some difference, but overall, it's getting very close. So now we are moving up to larger animals. In this case, we are using a mini pig for this kind of studies. We are collaborating with people at Emory, neurosurgeon at Emory. We are trying to apply this multi-tubular nerve conduit to really just repair a fissure nerve, actually, on the face of this pig, actually. Yeah, so that's the study for the next 5 years on this renewed grant. Finally, I'm using one slide to talk about wound dressing and dural tissue regeneration. That's a very important subject. And in this particular case, we developed a way to align the fibers into this radial fashion instead of this uniaxial alignment. In this case, the fiber is going from center to the peripheral, so in this kind of orientation. What's the advantage? Well, you can imagine if you apply this kind of scaffold as a patch on a wound, this wound could be like the dural defect during the brain surgery, okay? And the cells from the healthy tissue in the surrounding area will be able to migrate, actually, across this radially aligned fibers. So eventually will cross over and close this wound very easily and quickly. So that's basically the idea. As you can see over here, when you apply this patch to an ex vivo model, actually, you can see this void, actually, eventually could be just eliminated within a relatively short period of time, only like a few days. If you use random fibers, this could take weeks, actually. Still have a void over there. So the reason I want to mention this at the very beginning, because the student who did this study was an MD, PhD student in my group at WashU, and he started a company after graduation, and now all of these kind of scaffolding materials are already in clinical use. Actually, they have a company called Acera Surgical. Actually, they are already commercializing these kind of scaffolds for that kind of applications. So I think that's the end of my talk. I will be more than happy to answer your question. Thank you. We only have 2 people left anyway. Yeah.
Thank you for a great talk. Thank you, Professor Xia, for the great talk. I'm interested in the first part of the page.
Yeah.
I'm curious, have your team looked at the biocompatibility of the patch?
The biocompatibility is not the issue because they are fabricated from biocompatible polymers like PCl, PLGA, those kind of polymers. So we don't worry about those things. We do use some solvents during the processing, but those solvents are typically removed actually during at the end of the fabrication. So we don't worry about those. So the reason, for example, the last one, this was so quickly commercialized because the materials we are using is just the PLGA, PCl, those kind of polymers. We don't use exotic materials or only like FDA approved polymers. Yeah, so biocompatibility is not going to be an issue. Yeah. Yeah.
Any questions?
Yeah.
One other question I had was, you used femtosecond laser.
Yeah.
In that particular.
That's really nice tool, actually, I have to say.
That's, in fact, yeah, it's a heavily used tool.
Yeah.
One of the questions is that, what are the dimensions that you're successfully able to handle using femtosec laser?
Okay, well, for us, because of the size of the cell, we want our diameter to be about like 50 micrometers to like maybe 300 micrometers. It's relatively big, actually. Yeah, it's easy to do with the femtosecond laser. We don't want to go to like micrometer or this kind of scale, right? Yeah, at least should be 10 micrometer, yeah.
It's very interesting how uniformly it's all.
That's really impressive. I have one, this is okay.
So
if we look at that, it's pretty nice, actually.
Yes.
It's very nice, actually, yeah. This kind of like side wall is what really we prefer, actually. Instead of like a straight wall, we want them to be tapered like that way.
Right.
So they're going to form like self-locked like junctions.
Yeah,
when you have tissues, ingrowth into these channels. Yeah, it's a pretty nice tool,
Yeah, great work. Thank you, Professor.
Thank you, thank you.
Appreciate you coming. Let's thank Professor Xia one more time.
All right, thank you. Yeah, appreciate it. Next time I should choose a different topic.